In this video, we will introduce differential equations and the techniques for solving some differential equations. Basically, differential equations, or DE in short, are equations that contain variables and their respective derivatives. In the simplest sense, even the equation of dy over dx equals to x is considered a differential equation, although it is usually seen in integration problems. Differential equations can thus be thought of as a more general form of integration, much like doing the reverse of implicit differentiation. DEs can take many forms, but in the H2 syllabus, we are only required to know how to solve the following three types of differential equations, which we will go through in details in the coming slides. The first technique for solving DEs is when the variables, which are usually x and y, can be written as a product of separate functions of x and y, or dy dx equals to fx times gy. To solve this type of DE, we simply have to separate the variables into two sides of the equation and integrate the terms on both sides separately to obtain the solution. Note that although we have performed integration on both sides, we only need to put the integration constant c on one side of the solution equation. This is because integration constants are arbitrary and we can combine the two constants into a single term. When we solve for the DE without finding the value of c, this solution is called the general solution. However, if the question provides us with some values of x and y for us to find c, then the solution is called the particular solution. As an illustration to this solution method, for this DE, we can separate it into integrating 1 over sine y equals to integrate ex dx. This second DE can be separated into integration of 1 over y minus 2 dy equals to integration of x plus 2 dx. And this last equation over here can be separated into integration of y squared plus 1 dy equals to integrate sine x dx. And all of these separated forms can be integrated very easily to obtain the solutions. In example 1, we are now required to solve this DE over here, which we can see it is clearly a form which we can easily separate the variables since it is y multiplied by ln x. So a function of y and a function of x multiplied together, and we can separate them very easily. So we will have integration of 1 over y dy equals to integration of ln x dx, which we can integrate separately. So on the left hand side, we will end up with ln of mod y, and on the right hand side, we have to make use of integration by parts to give us x ln x minus integration of x times 1 over x dx. And upon solving, we will end up with x ln x minus x plus c. And therefore, we can say that mod y equals to e to the power of x ln x minus x plus c. However, this plus c in the power is not a very nice term, so we tend to want to write it as a. So we get a e x ln x minus x. And also, this modulus isn't very nice as well. I can rewrite this entire equation as y equals to plus minus a e x ln x minus x, which again I can rename the arbitrary constant over here into b e to the power of x ln x minus x, where b is equals to plus minus a, which is equals to plus minus e to the power of c. In example 2, we are now required to solve this DE, but not just for the general solution, instead for the particular solution, since we are given a set of x and y values that we can substitute into our general solution to obtain the particular solution. So let's solve for the general solution first. By rewriting this DE, we will end up with integration of 1 over y squared plus 1 dy equals to integration of 1 dx. And thus, integrating both sides, I will end up with tangent inverse y equals to x plus c. And I can rewrite it as y equals to tangent of x plus c. Now, I'm going to substitute x and y in when x is equals to pi over 8, y is equals to 1 to obtain the value of c. So I get tangent inverse 1 equals to pi over 8 plus c. And tangent inverse 1 is pi over 4. So pi over 4 equals to pi over 8 plus c. Therefore, I end up with c equals to pi over 8, which means the particular solution, or PS in short, is y equals to tangent x plus pi over 8. And that's it. The second type of DE that we need to know how to solve is the second order DE of the form d2y over dx squared equals to fx. Essentially, this is a double derivative and we can solve it by integrating it twice. The general solution of this type of DE will have two integration constants, c and d, because we are integrating it twice, meaning that the first integration constant c will be integrated to give us the second integration constant d. In example 3, we are asked to solve this second order ODE. So let's perform double integration. The first integration will give us dy over dx, which is equals to integration of 1 over x dx. And integrating this gives us ln x plus c. Next, y will be equals to integrate ln x plus c dx, which we can integrate using integration by parts for ln x to give us x ln x minus integration of x times 1 over x dx plus integrating c dx. And thus, this gives us x ln x minus x plus cx plus d. And I can group these two terms together since both of them are x terms to give x ln x plus c minus 1 x plus d. And I can again rename this c minus 1 so that it becomes slightly neater into x ln x plus bx plus d, where b is in fact just c minus 1. In some DEs, the variables cannot be separated, and thus we cannot solve them using the earlier methods. But we can make use of appropriate substitutions to transform these DEs into simpler forms which can be solved with our existing knowledge. In questions that require solution by substitution, the substitutions will always be given to us by the question. The hard part is to reduce them into the required forms. For example, we have this DE and we are required to make use of this substitution, y equals to ux plus 2, to reduce the DE into this particular form, which is what we are familiar with solving. To solve the transformation, we first differentiate the given substitution and make du dx the subject. This is because we want to make a substitution for it later on. Now, we can substitute both the given substitution and its derivative into the original DE. Since u becomes y, we do not change the x, and we substitute du dx into the equation. Also, we will change the ux term into y minus 2, as given by the original substitution. Note that in this particular example, we do not have to substitute the two u's over here and here because they will eventually cancel out nicely for us. Now, we can simplify this substituted equation and eventually show that it will be of the same form as the DE that the question has asked us to reduce to. So from this form, we can see that it is equals to the form that the question has asked us to prove. In example 4, we are given this DE which we cannot solve using our existing technique. So we are also given a substitution to help us reduce the dE into this form, which can be solved. Now let's perform the substitution to transform this dE into this dE. So first thing to do is to differentiate the given substitution. We have u equals to x squared plus y squared. This means that du over dx is equals to 2x plus 2y dy over dx. And note that in the original dE, we have this term over here, y dy dx, which is present over here as well. Thus, it will be easier if we can make y dy dx the subject over here. So y dy over dx will be equals to half du over dx minus x. Now let's call this equation 1, and I'm going to substitute equation 1 into the original dE. And therefore, I will end up with half du over dx minus x plus x equals to square root of x squared plus y squared is in fact u. So I have a square root of u over here. Therefore, if I reduce and cancel out the two x's, this equation becomes du over dx equals to 2 square root of u. And I have thus shown that this dE can be reduced into this simpler form over here. Next, we are required to solve this dE. So let's perform our variable separable technique. Integration of 1 over 2 square root u du equals to integrate dx. And if we integrate both sides separately, I will end up with square root u equals to x plus c. And therefore, if I square both sides, I get u equals to x plus c squared. Now, take note that u is a variable that we have introduced through a substitution, and the original variables are x and y. Therefore, I cannot simply stop my solution over here, but instead, I have to change it back into in terms of x and y. Therefore, this becomes x squared plus y squared for u, since we know that u is equals to x squared plus y squared. It will be equals to x squared plus 2cx plus c squared. And the x squared will cancel out nicely for us. We are left with y squared equals to 2cx plus c squared. And if we want to make y the subject, we will get y equals to plus minus square root of 2cx plus c squared. And that's it. When we solve for the general solutions of a dE, the value of the integration constant plays a huge part in determining the shape of the solution curve. When we use certain critical values for the integration constant, we will get vastly different types of curves. These curves with different shapes but from the same general solution are called the family of solution curves. For example, if we have the general solution y equals to x plus a times of e to the power of x, and when a equals to 0, we will end up with y equals to x, which is a straight line. If a is a positive number, say if we have a equals to 1, we will have the general solution becoming a particular solution of y equals to x plus e to the power of x, which is this red curve over here. Finally, if a is negative, let's say a is equals to minus 1, we will get y equals to x minus ex, which is this blue curve over here. Note that we have to choose values of a that will give us different fundamental shapes of the curves, like what we have shown over here. If we choose, say, a equals to 1 and a equals to 2, where a equals to 2 gives us y equals to x plus 2ex, the resulting graph will look something like this, which is of the same fundamental shape as the earlier case of a equals to 1, and thus they are not considered different members of the family of solution curves. In example 5, we are asked to solve this dE and subsequently sketch 3 member curves to represent the family of solution curves. So let's solve the dE first. It can be solved using variable separable, so we have integrate 1 over y plus 1 dy equals to integrate dx. And therefore, we get ln of mod y plus 1 equals to x plus c. And if we perform a lot more simplifications, we will end up with y plus 1 equals to a e x, where a is in fact plus minus e to the power of c. And therefore, we know that we can write it as y equals to minus 1 plus a e x. Now for the family of solution curves, we can first let a equals to 0. We will end up with y equals to minus 1, which looks like this. And this is when a is equals to 0. Next, I can let a be a positive number. And if a is a positive number, I will get something like this. And I can also let a be a negative number, which will thus give me a shape that looks like this. And thus, this is the family of solution curves required.